All right, let's dive into something kind of weird in the world of digital security. How can something be perfectly encrypted, yet you can still see it in plain sight? We're going to follow that one little flaw all the way down a rabbit hole that leads to the mathematical heart of, well, basically all modern cryptography. And to get what I'm talking about, you don't need a PhD in cryptography. Seriously, you just need to look at this next image. So, on the left, you've got the original picture of Tux, the Linux penguin. Pretty standard. On the right, that same exact image has been encrypted. I mean, the pixels are all scrambled up into this chaotic mess of color. But wait a second, something is really off here, right? We can still see the penguin. So, yeah, that's the big question, isn't it? If this thing is truly encrypted, how is this even possible? If all the data is supposed to be scrambled, why on earth can we still see the penguin? Well, the answer is a tiny flaw in how it was encrypted. This specific method, it's called electronic codebook or ECB, has this simple but totally fatal weakness. It encrypts each identical block of the image all by itself. So think about it. Every chunk of white belly in the original picture becomes the exact same scrambled block of colors on the right. The pattern of the original just leaks right through the encryption. Okay, so how do you fix a flaw like that? If letting each block do its own thing is the problem, what's to fix? Well, you've got to make them talk to each other. You have to chain them together. And that's done with a method called cipher block chaining, or CBC. Now here's where it gets really clever. Before you encrypt that first block, you mix it up with some random data. Then you encrypt it. But the real magic is what happens next. The result of that encryption gets used to mix with the second block before it gets encrypted. It creates this chain reaction. It's like a domino effect for encryption. Now, every single block's encryption depends on the one that came right before it, which guarantees that even two identical blocks of that white belly will look totally different in the end. And boom, the penguin is finally hidden. So we've fixed the pattern problem between the blocks, which is great. But that just brings up another question. What's actually happening inside each one of those blocks to scramble the data in the first place? What's the little engine in there that's actually doing all the hard work? Well, at the very heart of that engine, there's a component called an S-box, or a substitution box. The easiest way to think about it is like a super secret codebook. It takes one chunk of data as an input and just swaps it out for a completely different set of output data based on a fixed table. This substitution is what makes the whole thing unpredictable and really, really hard to guess. And its whole reason for being, its entire job, it's to create something cryptographers call confusion. It's designed to completely obscure the relationship between the secret key you're using and the final scrambled text. It just tangles them up so badly that an attacker can't just work backward to figure out your key. But what if attackers don't even try to guess the key? What if, instead, they try to break the S-box's underlying math? Because when you strip everything else away, that's all this is. It's just math. And this is a really crucial point. An S-box isn't some magic black box. It's a mathematical function. And just like any other function, you can describe it with a system of equations. And if an attacker can solve those equations, well, they can break the entire cipher. This brings us to a really sophisticated threat, the algebraic attack. So instead of just guessing the key over and over, an attacker writes out the cipher's S-boxes as this giant system of equations, and then tries to solve for the variables that represent the key. It's kind of like trying to find a mathematical skeleton key that unlocks the whole thing. So, how do we measure how tough an S-box is against this kind of attack? Cryptographers call it algebraic immunity. You can think of it like a durability score for the S-box's math. See, some mathematical equations are just simpler or weaker than others, and they can give an attacker a foothold. A really strong S-box has very few or even zero of these weak spots, which makes it incredibly difficult to solve. And that leads us to the central challenge for all cipher designers. How do you actually forge an S-box with the highest possible algebraic immunity? This is where the real mathematical arms race begins. So today's researchers are on this constant hunt for mathematically perfect S-boxes. They're not just counting the weak spots in the old designs, they are actively engineering new S-boxes that are built from the ground up to have zero of these specific vulnerabilities. Things with names like bi-affine or quadratic equations, which are just known to be easier for attackers to solve. And this table here, it shows you the trade-offs perfectly. Take a look at the standard inverse S-box on the bottom row. It has a high algebraic degree, which is good. It means it's complex. But look, it comes with 29 known weak spots.
Now compare that to the ones right above it. They were specifically designed to have 0 of those weak spots, making them way more resilient to this kind of attack, even if their overall complexity is a little bit lower. It's this constant balancing act.
Okay, so exponents, polynomial equations, why should you care about any of this super academic, deep in the weeds research? What does it actually mean for you and your data?
It means that the security of our digital world, it isn't some static thing. It's a never-ending contest. It's an arms race. Cipher designers build stronger mathematical walls, and attackers or crypto analysts find clever new ways to tear them down. And that cycle is what drives innovation and ultimately makes our encryption stronger. And that, right there, is what this all boils down to. That digital lock that protects your bank account, your private messages, your personal files, it isn't just a piece of software. It's this complex structure built on a deep, deep foundation of mathematics. And its strength comes from this intense, fundamental research into these tiny, hidden components like the S-box.
And this search is far from over. I mean, it's actually speeding up. With new threats looming on the horizon, I'm talking quantum computers, AI-powered attacks, the need for even more resilient S-boxes is more urgent than ever. The quest for this kind of mathematical perfection is ongoing, which leaves us with one final thought. What's going to be the next breakthrough in this hidden but absolutely essential world of cryptographic design?